This is a tutorial for the Hooke's Law lab, which is right here in my grade 11-12 physics simulations. So if we click on it, you've got this spring that's sitting up here, and you can adjust the spring constant between 1 and 20 newtons per meter. I guess we'll keep it on 10. And you can click and drag any of these weights if you want, and they'll just go on to the end of the spring. You can adjust the damping too. If you have zero damping, I'll just reset it to stop it moving. If you have zero damping, though, it's just going to move up and down forever, which is great for showing periodic motion, which my simulation can also do, but we'll get to that. So I'm going to add a little bit of damping here, so we'll actually slow down and reach some new compression. And the way the lab simulation works is that once it stops moving, you can click this plus, and this will add a point to the extension on the x-axis, force in the spring on the y-axis graph. And you can add different weights to new extensions. We'll wait for it to steady and stop, and you can add another point. And you can keep doing this. Maybe I'll increase the damping so it hopefully stops a little quicker. And once you've got enough points, you can actually click and drag in the graph a line of best fit. And you can see that my line of best fit, I got 9.7 newtons per meter for my spring constant, which is pretty close to the 10 here on the bar. Now, you can click here to reset it. If you click on KLab, it actually gives you a random value. All right, so you can perform the exact same experiment. And we'll just, I'm not really going to wait for them. We'll just do this quickly. But you guys get the idea. You can do the exact same experiment by putting different weights on it. And then whatever. Then you can just draw your line of best fit, and you can get, I got 14.71. If I unselect that, yeah, the answer is 15, so I got very close. So it's a very quick way for kids to simulate the Hooke's Law. There's a couple other things you can show on this. The first one, let's just reset this. The first one is a force versus time graph. So if we remove damping and I put 0.5 in, you can show that periodic motion. Okay, if it's too fast for you, you can slow it down. When you adjust the speed, it actually resets the graph, but you can see we got a nice slow graph here for force time. If you want to show damped harmonic motion, you can of course just add some damping. Just add a little bit to make it underdamped. And actually we'll speed the whole thing up a little bit. And you can see we get our very, very slightly damped harmonic motion here. And of course you can overdamp it as well. And just let that go, and you can get whatever type of graph you want that you're trying to demonstrate. The final thing you can do in this simulation is an energy graph. So maybe I'll put 1 kilogram on it again, and we'll just let it go. This is a bit fast, so I'm actually going to slow the whole thing right down. And you can see the change in energy from between EG, EK, and EE as it goes to, I guess, this is max height. So at the maximum height, you can see all of the energy is gravitational potential. And if you look at the graph here, our EG, which is our red line, is maximum, while our EK and EE are minimum. And then we could continue on until it's at the maximum extension of the spring. As that 1 kilogram goes down to the bottom. Now we have, of course, maximum elastic potential energy and minimum kinetic and gravitational potential in the center. And that is the Hooke's Law simulation.